It's nice to have Dimitri Papadimitriou with us. So Dimitri is working as a professor at the University of Antwerp in Belgium, and I will speak about stochastic nonlinear alternative multiplier, I will say ADMM for nonlinear composite problems, alternative direction method multiplier, something like that. And I will let the floor to you, Dimitri.
Yeah, thank you, Fabien. Thanks for the introduction. Thanks everyone for attending this session, and thanks for the invitation. So I hope that this 1 hour presentation will be raising interesting discussions. So I'm going to present here ongoing work on the stochastic nonlinear ADMM methods for nonlinear composite problems. So the structure of the talk is going to be as follows. So I'm going to provide here first an introduction, then dig a bit into the problem formulation in order to get positioning against the prior and related work in the literature. I will present actually then first the exact or deterministic variant of this algorithm, which is also innovative on its own right, and then switch directly to the stochastic nonlinear ADMM variant. I will then provide a demonstration of the convergence properties of these methods. And then one of the use cases we have, and probably some of the interesting results we are working on, is not on machine learning, is on dynamic traffic assignment problems coming out of logistics. So I will start then first with the introduction and motivation, backgrounds, and examples. So the main problem we are dealing with is actually the minimization of this function phi of u, which is composed of 3 terms: a function f, which is a proper l.s.c function, the function g, which is also a proper lower semi-continuous function, which are both actually not necessarily differentiable. And then one of the major characteristics of our problems is that this function g depends on a nonlinear differential mapping C. I think this is one of the distinguishing property of this problem we are aiming at solving. In addition to this, we have a term as part of the objective, which is non-convex but smooth, the function h, and which has LH Lipschitz continuous gradients. So why is this problem actually of interest? Well, actually, first of all, it has a generic nature and a very wide applicability. I may cite here computer science, the problem that I mentioned in logistic, and more generally speaking, network optimization is this dynamic traffic assignment problem. It has also applicability in image processing, delayering, denoising, and various forms of segmentation. And then the stochasticity, of course, has an interest in its own right in statistical learning, where the minimization of regularized empirical average of composite function is common duty. What are, generally speaking, actually the need for moving beyond what we have? That would be a kind of generic question. Well, we know actually the basic limits of existing splitting methods, the ALM, the augmented Lagrangian methods, where the quadratic penalty destroys actually the splitting of the X a bit. So it improves convergence, but can't actually take advantage of both your decomposition and methods of multipliers. And then, well, actually the core topic here is where are the limits of existing ADMM methods, alternating direction methods of multipliers, well, which combine actually dual decomposition in ALM. Actually, there was a method which was meant for overcoming the limitation of the previous one. Is that actually standard ADMM, in particular linear ones may still exhibit slow convergence. One of the reasons is that it still requires exact solutions of subproblems at each of the iterations. And then, well, the motivation of the problem, as I presented, in most applications, we have nonlinear composite functions which are non-smooth, and the operator C, as presented in my previous slide here, typically is often nonlinear. So I spoke about one of these applications, and let me go a bit further, because people may say, well, what's so specific about this? Well, typically in this dynamic traffic assignment problem, you have a traffic matrix, an amount of goods or devices to bring from point A to B, performance function, and then a topology, and you want to perform a path computation and selection before performing a dynamic network loading, where actually you are transporting all these goods from A to B. So it's a method actually to compute the path-dependent throughput delays on those next path. A method to determine how these path flows will induce actually time-dependent outflow delays and so forth. And well, in this DTA problem, typically what you have, but this is not part of this talk, is you would have actually to determine if and when performance criteria are being met. So this is typically the rather general formulation. What you have is you have a load-dependent utility non-concave function. Well, typically you have an S-shaped utility function, for instance, which is risk-seeking, and then afterwards risk-averse, and a bandwidth utility function, if you want, for instance. So this is more for, I would say, more communication network problems. And then you see directly actually the type of, we will transform this problem in the last part of this talk, but you see already actually the components coming in. You have non-convex constraints here, and you have actually a non-convex objective. And we'll see actually how the method that we are bringing in enables to handle these classes of problems. We'll come to this later with more details. As said, we can also deal with phase retrieval problems. We do not have yet numerical results on this, so I'm probably going to spare a bit of time and not, I would say, delve into the problem formulation. But it's certainly something that we have in mind for the future, and the same for the blind deconvolution problem. You have actually these nice problem formulations which are getting actually your interest too in image processing. So, well, before actually going into further details, well, no, actually we went to the introduction, so I'm going to introduce the theoretical part of the work. Well, actually, most of the work here is being, I would say, centered on proximity operators definition. So the proximity operator of a proper lower semi-continuous convex function f is defined by the expression 13 here. And it is characterized by this identity, where you have actually, if when p equals the prox f of x, and similar to x minus p belonging to the subdifferential of f at p, as given by this expression. Some of the demonstration we have can also be realized by means of the Moreau proximal envelope. And finally, we also make use of the conjugate of the function f, as given by this expression, where you map u to the supremum of the scalar product of u of a minus f of a. Well, you can find actually, and this is a website that I like to share, http proximity-operator.net. It's an interesting, I would say, website where you can find actually many examples of application of proximity operator. Well, in particular, this is of interest to us because when f is the indicator function of v, then the prox of v is a projection of x onto v. And if, in another, I would say, a classical example, if g of x is the L1 norm of x, which is the sum of the absolute values of its component, then actually the proximity operator x of g is the sine of x times the max of x minus gamma. And this is the type of, I would say, graph, a function graph that you can obtain by using the examples on this website. So again, actually here, the problem is to minimize over U, the function phi of U with these three components. Important, the operator C is nonlinear and the differential mapping. Function H is differentiable but non-convex. And F and G are proper lower semi-continuous functions, which are not necessarily differentiable, so non-smooth. That makes actually a very, I would say, and the objectives we have is to find an epsilon first order optimality condition, which is going to be solving the min-max problem given by this pair of expression, where B of epsilon is a closed ball of with radius epsilon. And one can easily recognize out of this the Karush-Kuntukier condition when epsilon equals 0. GC of U here is a Jacobian of the operator of C. The objective too, as I said before already, is to devise a nonlinear ADMM method. So at each iteration, we'll separately evaluate the non-smooth component F and G via their proximity operators. We're going to evaluate the smooth component H via its gradients, and the nonlinear operator C via its values. And we are going to extend this in a stochastic setting. Cool. And then the third objective, as you may foresee, is to characterize the convergence in terms of gradient mapping and feasibility properties, and show how various applications can be actually reformulated as special cases of the generic problem. And I will focus on the DTA because I think that's probably one of the interesting cases here. So people may wonder what has been the history of I would say of using all these techniques since I would say a decade. The first, I would say, particular case which is important to mention is the model 1, where actually H equals 0, and then you get actually this reduced problem where you have no H component as part of the objective. And Valkonen has actually investigated a nonlinear version of the well-known Chambol-Pock algorithm by defining actually these update rules. And actually, what is the major limit is actually in the work of Valkonen in 2014, it mandates that the conjugate of G is strongly convex on the set YNL. And mandating that actually in most applications that the set YNL correspond to the space Y, and hence G being differentiable. So that's I would say big piece of work which has been done on this reduced problem, but you see directly the limitations. The model number 2 is based on augmenting the ALM, or I would say extending the ALM methods. Well, there has been many work on this. Typically, actually, I think I've cited the latest, I would say, main methods which have been dealing with this extension or enhancement of the ALM methods. But actually, they all share actually the following limitations. Well, I'm not saying that also our methods has limitations, but what I'm saying is the ones that have been already crystallized in and well understood. There's a primal steps. Actually, one of the issues is that the primal step requires subsolver, and so the question has always been whether the involvement and the implication of requiring a subsolver for the primal steps, and so is inducing an increase of the computational cost, but it's also increasing some of the things that come into the loop where that each of these variants would be able actually to focus on particular case of one of our problems. And actually, they are by nature non-splitting methods. So the question has always been, you could actually also accelerate some of these methods, but actually not falling anymore within the splitting category. And then an interesting work has been based on these, what has been called the linearized version, or because where C and D are linear mappings in the conditions here. And the lin Liu and Sous in 2011, so more than 10 years ago, I have proposed a linear alternating direction method with these update rules for the variables and the duals. And actually here, what are the major limits? Well, as the name indicates, of course, the C and D operator, the matrix C and D are linear. It's a convex optimization problem, and you have no component, non-convex component as part of the objective. So all in all, actually, well, this justifies somehow the need for extending what we have in terms of methods from the scientific and technical literature. So, well, let me start then with the well, having justified actually why we do all this work, probably also dealing first with a deterministic nonlinear ADMM and provide a bit of give a sense of these conversion properties. This is also, I would say, a genuine part of the work here. So, as I said, we want to have a full splitting method. So at each iteration, we're going to have an evaluation of the non-smooth component f and g via their proximity operators. We're going to evaluate the smooth component h by its gradient and the nonlinear operator c by its value, and all this being done separately. So the demonstration of the convergence properties involves a couple of lemmas. The first one is the an extended Moreau decomposition lemma, where actually these two identities are going to be used as part of the demonstration that I'm not going to be showing, but I'm just mentioning those because this is typically a very interesting way of, I would say, exploiting these decomposition methods and prove its the properties of our algorithm. We also exploit actually as part of one theorem from Patrick Louis-Combet, which has been proposed in one of his papers in 2005, but where actually his theorem is being limited to the case where the map C is linear. So we are proposed actually to this lemma here that we are proposing here is extending actually this theorem to the case where the map C is nonlinear. And then you see actually the introduction here that for every beta, we're going to be defining an operator G beta from the space X, the composition of space X and Y. Actually, the pair of variables U lambda is going to be projected on the supremum of Y over Y of this expression. And we assume that actually G beta is a differentiable function with respect to the variable U. And the gradient over U of the G beta is going to be given by the conjugate of the Jacobian of U times the proximal, the prox beta over beta minus 1 G star of this expression. So you see actually that we are extending actually also existing work in actually obtaining the convergence properties of our algorithm. Well, people can find actually the full demonstration of this in our paper. Then actually I want to make two remarks here. Well, because actually one of the questions that is going to come out sooner or later is we have several examples in the literature where G beta would admit actually a closed form expression. That's the first thing, which is important for numerical execution. And actually, since the function G beta is a smooth approximation of G, then we have various numerical methods that can be exploited in order to by means of this smoothing technique. So it doesn't prevent actually it doesn't limit actually the computational, I would say, nature of the algorithm that we are bringing. Another important, I would say, ingredient is the definition of the gradient mapping. So we are first, let's given beta and gamma larger than 0, we are going to be defining the operator f beta, which is going to project, I would say, push u lambda of on the composite of h of u and g beta u of lambda, and then the gradient mapping. And this is also an important component here, because actually the gradient mapping has to be understood as reducing to the usual gradient when we're going to be minimizing a single differentiable function h. And this is a core, I would say, remark here, is that in non-convex optimization, we know very well the relationship between the gradient mapping and stationary points when G corresponds, when there is no G term as part of the objective. But actually, this is not the case where when you have a G component as part of it, and this is going to be developed as part of our first theorem. No, and this can be given here when G corresponds is absent. Suppose that you have U equal U plus, then U is going to be a stationary point of expression 18. So 18, the expression 18 is here. So just as a remember, or probably here. So and then what you're going to be having, is you're going to be a stationary point of our original problem, and indeed when it will follow from the absence of the term G in the as part of the objective that f of u will be limited to these two elements, these two components as part of the objective, and the grade of G beta over u will be equal to 0. Hence, actually, you're going to have a definition of u plus given by this expression. And by the identity, the proximity operator identity, you can show that u is going to be a stationary point of the function phi. It's also important to mention actually the relation between the gradient mapping and the function value f beta. Actually, this has been obtained by extending lemma 2 of a paper published by Bolt in 2014. So actually what he did, of course, is we did this for the deterministic case, as shown by expression here 31. But we also extended this for the stochastic case. So actually what it bounds actually is the L2 norm of G beta gamma, and it does this equivalently for in the stochastic case where delta beta here is actually a random variable, which is actually going to be the essential element that you're going to be bringing in order to extend the deterministic setting to a stochastic setting. Having said this, so we are also operating three major, I would say, assumptions as part of the work. So the first is that the sub-differential of G delta G is bounded by a constant kappa. And we have actually an equivalence between these two assumptions. The Jacobian of the operator C is going to be mu C Lipschitz. And it's equivalent to make an uniform regularity, impose a uniform regularity condition of C on the domain of a function f. And an important aspect which has been, which is playing here in terms of what we might be calling a geometric actually interpretation of all the development we do here, is when the space Y corresponds to Rm. These assumptions are actually is equivalent to the Mangaresen form of its condition of C on the domain of F. And then finally, an assumption A3, which assumes that for each variable lambda in the space Y and values of beta, the gradient of over U of G beta is going to be lambda L beta lambda Lipschitz continuous. So we assume lambda L beta Lipschitz continuity of the gradient of the function G beta. So this is the exact algorithm we have. You have, as you may assume, we have the settings of certain parameters. And then initialization of U0 and lambda 0, so the primal and the dual. And then a couple of parameters, which is going to be tuning actually the execution of the primal step and the auxiliary step. The important actually in this type of work is the definition of the auxiliary step in order to facilitate the computation of the dual step, which is conditioned on the findings of a value 2 belonging to an interval 0 over sigma kappa k minus 1, so that actually these conditions are being met. And the whole work actually in determining this sort of nonlinear ADMM is the specification of these conditions and the findings of this condition in order to have the dual step being effectively computed. And this is what you see. You are fixing actually a certain number of iterations. You are computing the value W, Y star K, and UK plus 1. You have an auxiliary step associated to it. And then actually from there, you are computing actually the dual variable lambda 2, meeting actually, so that 2 means actually these conditions. Y2 star means this condition. And then you're updating the value sigma k and the dual variable lambda k plus 1. Having said this, well, actually, I'm not going to go in the specific, well, in the demonstration of the properties of the exact algorithm, just state actually the major theorem. So first, what you have to recall is the definition of h beta, the function g beta that I gave here, which is actually given by this expression, and then the function value f beta, which is the sum of g beta plus h of u. And the convergence proof rely on the key result. Whenever actually the gradient mapping is going to be close to 0, the feasibility is going to be close to 0, then actually the pair u plus gradient and the gradient of h beta is going to be close to a certain point. And so actually this is the general theorem that we have. Suppose that the assumptions are being satisfied. You are setting let's say v hash being equal to the gradient of h beta with u plus defined by this expression. And then you are supposing actually that you have a nice behavior of your parameter gamma, which is determined by the Lipschitz constants of h and g beta. Then actually you can show that the norm of g beta gamma is bounded by epsilon. The feasibility is bounded by 2 epsilon, and in consequence, u plus v hash is going to be 2 epsilon, is going to be a 2 epsilon saddle point. Well, a lemma which is playing an important role, and I mention it because actually it's going to be extended in the stochastic case, is that suppose that these assumptions are being satisfied, setting actually these, this is just a notation, actually artifacts in order to simplify a bit the length of the expressions. Then actually you can show that this update rule here is being satisfied. And then the theorem, supposing that the assumptions A1, 2, 3 are satisfied, and you have an infinite number of iterations, then actually you can show that AK plus 1 is bounded by this expression. So as a consequence, actually, if the sequence A of k is bounded below, then you can show that the sequence of values that you're going to be obtaining for the objective phi of UK is going to be converging. And this inequality is going to be verified. So we are going to be showing that actually if the sequence gamma k is going to be monotonically decreasing, then for every value of n, you're going to be bounding actually the square of the norm of the difference between the iterates of UK plus 1 minus UK divided by gamma k, and the same for the auxiliary problem. And then if you choose actually a sequence gamma k such that these iterates actually decreasing as k increases, and this condition is being verified here, gamma square of gamma n square multiplied by the sum of the values of 1 over gamma will tend to infinite as the number of iterates of the algorithm goes to infinite. Then you're going to be showing that your sequence is going to be converging to 0 as the iteration k tends to infinite. You're going to have also this under the same condition. You're going to be showing that actually under the same condition as the point 2 here for gamma k and y being a finite dimensional space, then every cluster point is going to be a stationary point of the function phi. So we know now that the exact variant is converging. Let us show now what first the stochastic nonlinear ADMM it looks like. Well, let me first introduce a couple of definitions for that purpose. We have a probability space omega fp. Omega is a sample space, so the non-empty set of all possible outcomes. A set of events f, which define a sigma algebra on omega. Well, we shouldn't have been using the term sigma in the previous algorithm. It might be confusing with the notations. A subset, what is a sigma algebra on omega? It's a set of subsets that contains omega as a member and that is closed, uncountable, union, and complement. In the discrete case, it's important to mention that each event will comprise from a 0 to a finite number of outcomes. And we have the probability measure P, which is assigned to each event in a probability P in 0, 1, such that P omega equals none. Random variables. So here it's important to recapitulate the definition. We are going to call an x valued random variable, which is going to be a measurable function x from omega to space x, where x is going to be endowed by a Borel sigma algebra. And given a sequence of x valued random variables, fk is going to be f of Desjardins f of k here denotes a sigma algebra generated by the set ui I between 0 and k. And then in terms of just for notation, a of x is going to be denoting the expectation of the random variable x, and x, the expectation of the conditional expectation of x given the random variable y is going to be given by this expression here. So as a usual assumption, first is that we only know is first all the information on the function value of beta that is going to be available, such as its gradient is the information which is being made accessible by calls to a stochastic first order oracle, an SFO. And we're going to be making the standard, or taking the standard condition on the stochastic first order oracle. So we're going to assume that given U in the domain of f and a random element xi given by an unknown probability distribution, the sigma additive, we can actually generate stochastic estimates R u xi lambda of the gradient of f beta over u, such that actually the condition on the mean and the conditions on the variance are being met. So we are not introducing anything new here in terms of conditions or making it more or less restrictive than what you have in the literature. Actually, these conditions are the standard conditions on the mean of the stochastic estimate of the gradient and its variance, which are completely standard from literature. Another aspect to highlight is that we are going to be taking these, I mentioned this delta k variable, so it's a random variable from the space omega to x, which is going to belong to the Hilbert space L2 here of the x value random variable, such that actually the expectation over the square norm is finite. Well, I would say the prototypical example here is these, and I think the previous talk was also referring to it, is this regularized empirical average of composite functions. I think this is probably the prototypical or paradigmatic actually examples we can use for these kind of problems. So we are going to be supposing that the space Y is the composition of a finite family of real Hilbert spaces. We are going to take consider that for every I belonging to 1 over n, we're going to be setting a function gi from the space Y, which is going to be bound below by a proper logarithmic continuous convex function. And so we can set actually the map from V to the sum of the composite function gi on Vi. And then if we let's see actually this operator belonging actually be a differentiable smooth map with mu-C Lipschitz Jacobian, we're going to have actually a function g of c minus beta given by this sum of composite function gi over taken on ci minus beta I. And then you can have actually this the same actually type of, I would say, similar type of operation for the non-convex smooth function h, which is going to also to be given by a finite sum as expressed by this expression here, 1 over n1, the sum over I over hi. So, well, we have to dig progressively in the stochastic variance of these problems that we are handling. So first, well, we are going to define a random variable xi, which is it's a composite variable actually. We have a composite components ik and jk with uniform distribution. And then you can define actually the stochastic problems as being given here. So you have, you remember what I presented before. I do not know why it should be x here, sorry. So the minimization over phi is going to be, the expressions are going to be, that h of x is going to be the expectation over h of x xi, and the function g of c of x minus b is going to be given by the expectation of xi over gc of xi minus b over xi. That's actually the most general stochastic variance of the problem that we can come with. And you can have actually the case where the non-smooth, the non-convex component has no randomness. Having said this, well, now we're going to be extending our algorithm first and then show its conversion properties. So we can first actually define for the stochastic case, as we did for the exact one, these operators, h beta and g beta. And then start with the first proposition that if the stochastic gradient is being defined by, I take here the definition of the stochastic gradient as being given by R, so the gradient of the component h of jk plus n times the gradient over g beta on u of g beta, then actually the gradient of the function value of beta is going to be given by the expectation being taken over these components for each of these elements lambda ik here, and actually this is going to be corresponding to the gradient of the value, the function value f beta. So do we have a proof of this? Yes, we have. So what we can show here is that by simple computation of the conjugate function of g, given by this expression here, it's a composite function. So if we follow the definition of g beta as given by expression 28, for every value of for every lambda I from from 1 to n, and every u in the domain of f, we're going to be having actually an expression of the function g beta as given by 56 here, and then we can bring this down towards the sum of composite function g beta. Then if you use a definition of f beta, which is actually the sum of g beta plus hu, we're going to have a sum actually of composite function g beta I here and hi of u here. And so you can show that the gradient then of the functional value of f beta will be given by this expression, which shows actually the proof of this theorem. So now if you replace a full gradient by a mini batch gradient defined by this expression, where RK is going to be, you're going to take actually a number of data points or samples MK here, which is going to be larger than 1, and you're going to be summing the components. Where actually for each of the components you have the value which is being returned by the IM call to the SFO and the stochastic first order oracle at each of these iterations. And we assume that we have doing this over ID copies of the random variable xik and ik. Xik here, there is a typo. And so we get actually, again, the conditions on the stochastic estimate of the gradient are preserved by this definition of the mini batch of the gradient, this mini batch gradient definition. So one can show that actually the expectation taken over the mini batch gradient is going to be given by the gradient of the function value f beta k over uk. And you have again the condition that you put on the variance as being given by this expression here being met again. So you can show actually that the latest expression is being given by this lemma here, and how we can show this. So this last expression here is proven by this lemma S1. If you consider that for all values of the size of the mini batch that we have been taking, we are defining the random variable delta k being given by the sum over I of delta ki as being given by this difference, then we can show that the expectation of the square norm of these, the values of this variable is going to be bounded by the variance at iterate k divided by the number of elements in that sample. And this is being given by this proof here again. So we are going to be expanding, defining a gamma mk being given by the sum of the delta ki, and for this we get actually the definition that is going to be injected as part of this expectation here, expanding and then contracting in order to get this expression. Next, next actually it is the extension of the previous deterministic algorithm when injecting actually randomness, and you see actually the difference is very difficult to put them both on a single slide, but you see actually within this explanation of the algorithm that how actually the inclusion of randomness plays in extending actually the expressions of the update rule of the variables uk. And you see this delta k belonging to this Hilbert space. And then you see actually how this modifies actually the conditions for the computation at the dual steps, So now what you are going to be showing in this stochastic nonlinear ADMM is these convergence properties. I do not know, Fabian, how much time do I have? Hello?
Set it approximately, if you can take 5 to 10 minutes still. It would be nice to leave some time for questions.
Okay. Because now we're going to enter within the demonstration of the theorem and the main
So
theorem.
you can skip some details of the proofs.
I can skip. Okay. I thought people would be interested by the details of the demonstration. This is my.
Yeah, it's up to you. But
okay. No. Well, I'm gonna do something. I'm gonna spell out the theorem. So if you consider that at iterations k of the stochastic algorithm, we define actually the mini batch gradient RK here. We're gonna have the set of values of the stochastic gradient components as returned by EM call to the SFO, and assume that the size of your mini batch is lower bounded. That's a critical condition. Your size of your mini batch must be lower bounded by this value. You can then define actually this delta k as being defined by this difference between the mini batch and the gradient of f beta k over UK. And you are supposing that the assumption, core assumption 1, 2, 3 are satisfied, then you can prove actually this inequality here. I'm going to skip actually the details, because actually what is important is, in that case, again, what you can find is a convergence. Well, the expectation of the value of phi over xk is converging. It's UK here. But then what is important to show is that the expectation that we get over this value is bounded actually by the values that we get once you are computing actually over these iterates by taken by the 2 times the expectation over the square norm, plus an element given by 2 times the variance divided by the size of the mini batch sample, the size of the mini batch. And moreover, if the operator C is 2C Lipschitz continuous, we get this inequality. So I'm going to probably, as Fabian suggested, to not go in all the details of the demonstration, because it's quite, well, we have all the demonstrations here, but I'm going to skip this for the sake of time. And probably go in some elements of the properties. So as I said, the bounds, the properties of the bounds that we get depends on the size of the mini batch. And so what we have to do is to take a minimal size to this mini batch, of course. So by increasing the size of the mini batch, the error existing in estimating the gradient of f beta k will be decreasing. But no, of course, if that size mk becomes too large, then each iteration will be extremely expensive to compute due to the computation of the stochastic gradients. And as mk will be increasing, of course, one will progressively reach the deterministic rates of convergence. And what we can show is that all choice of the batch size show that mk will tend to infinite as the number of iterations will also tend to infinite. However, what we have determined is that in most situations this is unlikely to occur, because actually in most applications we need to find an epsilon approximate of the stationary point. You don't necessarily have to have an exactness of the values of the solution that you are being computing, and in second case, in machine learning, a lower precision is being allowed, and so and the values of epsilon is often much larger than the inverse of the size of the full gradient. Probably an important point that I want to mention, because I said how the algorithm compares in the situations of exact or deterministic problems. But what about actually in the stochastic setting? Well, actually in the stochastic setting, we have a bit of the same comparative analysis we can do. Most of the work which has been done, and I cite here also the major references in the convex and non-convex settings. Most of the problems are limited to situations where we have a linear operator C. And I must cite here a comparison when actually you have probably the 2 major, I would say, references in the domain in that space. Yang in 2013 it transformed in a stochastic variant when the components F1 and F2 were convex and the operator A and B linear. And then he showed that when you are performing the approximation of F1 by this expression and then apply an ADMM step to the approximate augmented Lagrangian, you can show that both objective and feasibility will converge to 0 under suitable conditions with a rate 1 over a square root of k. And actually, I extended that result when the function f1 and f2 are non-convex. Well, I would like to show this and compare against the rays that we are being obtained, which is actually very interesting, because what it shows is we are not that far theoretically about what we can obtain, provided that the size of the mini batch can be appropriately set, and this depends a lot in terms of the problems that we are being obtaining. Let me go. So I think I'm close to the end. Well, probably something that I wanted to show before closing is we wanted to compare against the multi-constraint DTA problem, and the result that we were obtaining by this. Well, we were able to obtain results for the exact or deterministic algorithm, also some results for the stochastic one. But what was one of our interests was to show how these methods actually being compared to the classical methods that people are being using by means of MIP solvers. So taking this problem here and trying to solve this over different instances after having done define a transformation of the variables, so that the load variables LA become actually given by this expression. So transforming actually the problem where you do not have any more nonlinear constraint, but non-convex constraint, but nonlinear ones, and test this over these topologies here. So you see the number for each of these topologies, you have the number of owners, number of arcs, and about n squared. The number of demands is being given. You have a definition of the non-convex disutility function we were using. We can transform in non-concave in case of a maximization problem. And this is the result that we were obtaining using the nonlinear ADMM methods. So we have for each of the topology the value of the initial objective, the feasibility, and showing that actually the feasibility decreases from a high value to almost zero in most of these instances, and the minimum objective value we're obtaining. Well, null load arcs is probably not that important for discussing here, but what I wanted to show is the computational time that we are being obtaining, which is rather competitive against, actually, this is what we wanted to know, because it was difficult to get a way of comparing these solutions. What we obtained were using a transformation by a variant of RLT reformulation linearization technique for this method here. Well, I'm skipping here all the details, and the comparison that we get when using the solving of this problem by means of the MIP solver instead of the nonlinear ADMM technique. And the interesting case or observation that we had was the cases where the nonlinear ADMM was the most effective has been the one where the RLT reformulation and the solving by means of the MIP solver is the least effective. So there is an interesting situation here that we obtain where actually probably there might be further work to be done in order to determine why the instance which is the most effective is solved, which is Germany here by the nonlinear ADMM algorithm, is the one which is the worst solved by the MIP solver and vice versa. We are not yet there in terms of understanding why this is happening, but there is certainly something that says that the methods can still be further, I would say, enhanced. Anyway, so the last point concerning this problem here, if I take this composite minimization problem and all these properties, if I take this class of methods, this nonlinear ADMM and its stochastic variant as indicated here, outperforms in terms of functionality whichever I would see prior work in this domain. And I cited Valkonen and Bolt, but we have also variants of linear ADMM, proxilinear ADMM, inexact ALMs, and all the features are there. So it remains actually to show in terms of numerical properties that we can first reach the expectation, also in stochastic settings, which is challenging, and actually how competitive it is against the more classical solution when transforming actually the problems into formulations which are solved by means of a MIP solver. And this is easily done. You just actually linearize the problem by means of RMT, you take your objective and use a piecewise linear approximation out of it with components, and our own MIP solver was able to solve this rather effectively. So this is what I have for this talk. I think I'm going to stop here. I will also send a version with some nits that needs to be updated as part of the talk. So please let me know if you have any question.
Yes, thank you, Dimitri. We are already running out of time, but I will still have time to take a few questions. I saw in the chat some questions from Sven Leifer, especially regarding are the convex formation of constraints 5 using this regression?
Je vais prendre la question. Le chat, il dit
la question est dans le chat.
Ouais.
Donc, il y a deux questions de Sven. Or Sven wants to add the question.
Yeah, it's maybe not an important question, but there may be.
No, it is. It is. I will constraint 5. You mean in the DTA problem, right?
Yeah, that's right.
Yeah, all right. Okay, I'm going to explain this. Let me take your question next to my screen, because so actually when you say constraint 5, here is this one, right? The delay.
Correct.
Yeah, right. Actually, here these constraints, when you take more than one demand, those are non-convex constraints. And actually, what has happened is taking this, the first, I would say, the major actually step that we got in order to have this solvable by MIP solver was this transformation here. Define a variable YA, which is 1 over the load, or kappa A, the capacity of the arc divided by the capacity arc minus the load. And then you can have actually a load variable LA, which is given by this expression. You are replacing this, and actually you go from non-convex constraint to actually bilinear constraints, because you're multiplying
which is still not, it's still non-linear, but you can at least have a convex relaxation.
Yeah, it becomes non-linear constraints. And actually, this can be solved by, it's not even RLT, it's actually it's a Markovian, we use actually Markovian envelopes, which is in this case going on to the same. And then our MIP solver was able to cope with this problem, because actually what we did was we didn't inject, of course, the analytic form of the utility, but a piecewise linear approximation out of it. We took each of the components. So it means that if you have a good idea about the shape of your utility function, you can still actually well approximate the value of the objective and solve this by means of a MIP solver. That was actually how we were able to compare, because what people have to know is in making numerical execution out of this, there is a very difficult way of getting actually values for a problem for which we have comparable values, and how the values that we obtain, how they can be compared against existing methods. In particular, if you take methods which are a nonlinear ADMM, which is not able to cope with a problem, how to compare actually the performance of the method we are proposing. Yeah. And that was one technique that we found in order to have something comparable. But that's actually the slide 44 here is quite a strength, I would say. It's quite a powerful transformation that we did over the initial problem here in order to bring this from a non-convex constraint, because they were unreducible, to nonlinear constraint. Of course, the objective remains on concave or non-convex, depending on whether you want to minimize this utility or maximize utility. But it was making it so that we could have a formulation that was numerically solvable by a MIP solver. And I think that's an interesting point to bring on this own, basically.
Okay. And maybe the last questions after, because it's really lunchtime, still by Sven, but I'll share the questions too. About the assumptions that you make, A1 to A3, so question 36, is there any way to ensure the assumption? Is there any way to make it, to ensure them in the constructive way?
Yeah, well,
yeah, so maybe I can expand on that a little bit. The question is really, the proof is very intricate, it's very detailed, but it seems to contain a lot of assumptions on the progress of the method.
Yeah.
And that's not really assumptions that are good. We like assumptions on the problem itself that I can check, and then have an algorithm that can handle or enforces or it implies these kinds of assumptions in a constructive way.
Right.
And so I don't see how to enforce, for example, 36
Yes.
In an algorithmic way. And that's what this question is really going after. And I think there were other cases too. Yeah.
Right. But I take this question as granted, and it's also one of the numerical algorithmic, I would say, challenge we have. Because it's very, I would say, it's already challenging to prove that if these conditions are met, then you are being converging as shown. But actually, then the question becomes, if you do this numerically, how are you going to be computing this in order to show that you're meeting your theoretical, I would say, or abstract algorithm? And I think that what I'm, and I say this without too many problems, too many troubles, is when numerically executed on nonlinear ADMM, we are applying our primal step or auxiliary step. This is relatively easy, or dual step, and then actually spend lots of time in order to show that these conditions are being met. It's not straightforward. It's not because an abstract algorithm as shown here has been laid out, that the numerical algorithm that comes towards it in order to show that for this specific application, the finding of the values of the duals based on the conditions that are being 36 here are being, this is absolutely non-trivial, even for when executing each of these iterations. Of course, what we have.
But do you enforce these conditions during the algorithm, during the
execution of the algorithm? Yes.
And how do you do that? So is there a practical way of doing that?
Well, maybe my question should be, what do you mean by practical? Do you mean that, do you think, because the question is, what you have to say is we have an interval over this value tau has to be taken. And then actually this value tau determines how the value of your dual variables lambdas are being set. And then these values needs to meet certain, I would say, conditions are given by 36. So
okay, and these conditions are easy to verify? That's what I'm asking.
Well, they are relatively easy to be verified, but actually they are consuming in the sense that you have to be sure that your algorithm is being converging it's not because you have bounds as this abstract algorithm tells you that you can necessarily have the numerical execution of the algorithm easy to be performing, because actually it depends on how the interval that you have to be considering over which your value tau will be falling into. And so now what has happened is you have to have a very good, I would say, numerical algorithm. And this is what we have been doing in terms of to determine that the execution is being meeting actually these conditions here. And it is not, well, the question is, when you say easy, it is it not actually being more complex than the initial problem that you are trying to solve? And actually the situation or the answer to this is no, it is more effective, but indeed it requires to have a really good understanding on how to handle the Jacobian over the value uk plus 1 here and its conjugate. Okay, this bound here is relatively actually straightforward because these are just parameters. The norm of the norm of the dual variables lambda k here is bounded again by parameters kappa, beta, theta divided by gamma k. What is a bit more involved here is this condition, and this condition is where actually the handling and goes over, because you are actually the bounds that this inequality is being determined by the Jacobian, the conjugate of the Jacobian, and the difference of the conjugate of the Jacobian here over successive iterates taken to the square norm divided by the values of the variables that you are being obtaining numerically over the different iterates. And this is the most difficult, I would say, if you ask about which complexity, this is the most actually difficult inequality to handle numerically. Yeah? In particular, if you take its stochastic variant.
Okay.
Okay. Thanks. Well, it's just to show where the difficulty stands, and in these conditions, the difficulty stands here. And unfortunately, this is where also if you extend this to a nonlinear, a stochastic condition, this is where also the conditions are being even given more difficult to have. 65 here is becoming even more involved when moving to the stochastic. Of course, and I must say something to probably to conclude on that question. It is a challenge to find this theoretically, this condition, but it's also a numerical challenge in order to find an effective and an efficient procedure to meet them at each of the iteration of the algorithm. Yes, certainly an important point. Any other questions from the audience? Is Sven has other?
I see the time, it's already 10:08, so I would suggest that we can continue the discussion in the backward room. So I can assign you, or you can join the backward room.
I will be in the room. I will be in the room.
Yeah, so we can continue the discussion in the backward room.